Hi there, welcome back this is lecture 2 of Fox. So just to remind you, last time we talked about discrete math and the theory of computing, and how discrete math is about discrete objects and reasoning about them. So today the goal is to introduce you to the main discrete objects that we'll be talking about in this class, and this whole notion about reasoning about discrete objects, i.e. to introduce you to the concept of a proof. Okay. So just remember from last time, I showed you, I gave you 3 challenge problems: the subset sum problem, the matching subset sum problem. So I hope you go ahead and try to solve this problem. There's $100 in it for you if you manage to find 2 sets of numbers within this collection of 100 numbers. If you can find 2 sets that match in terms of their sum, it's $100. Okay, then we talked about the domino problem and whether you can write a program to solve the domino puzzle problem. That's worth $1,000. Don't go for this problem in any way unless you really feel confident that I was wrong to pose this problem and I'm going to be shelling out the $1,000. It's just there to show you that this is a very hard problem. I don't believe that I'm going to be giving out that $1,000 anytime soon. $10 for a cartoon. Okay, but the main thing here is to show you how the relationship between how discrete math is used in both formulating and solving problems that would be relevant to a computer scientist. Okay. Today's theme is discrete objects and proof. Okay, we're going to talk about the 3 main types of discrete objects that we will focus on in this class and that are relevant for computer science. Those are sets, sequences, and graphs. And then I'm going to introduce you informally to the concept of a proof. We're going to prove several things. We'll prove something about that speed dating game or that speed dating club that we talked about. We'll prove something about when is a number even. We'll talk about remember I showed you that social network with 6 friends, and some are friends with other people and not friends with other people. So we'll show that no matter how you construct such a six friend network, there's going to be a little bit of structure in this 6 friend network. Either 3 will be mutual friends or 3 will be mutual enemies. Okay. So that'll give you some taste for proof, and I'll introduce you to a very, very important axiom, which is called the well-ordering principle, and we'll use this axiom to prove something, and we'll prove it in a very strange way. And it might be the first time you have seen, for many of you, that the square root of 2 is not a number that is easy to express as a fraction. Okay. In fact, it cannot be expressed as a fraction, and this is what led to the sort of development of the fact that there are numbers that are not rationals means that there's a whole set of numbers out there, and we need to develop a theory for such numbers, and that's the real number system. We won't get into the real number system. I just want to show you that the square root of 2 is not rational in the context of introducing you to proof. Okay, so let's begin. And what we will do is we will switch over to the board, because today we're going to be talking about mathematical things, and it generally tends to be useful to have something to write on anytime you are either listening to or talking about mathematical things. Okay, so discrete objects. So we're going to talk about sets, sequences, and graphs, and then we're going to wade into proofs. Okay, and I'll tell you about even squares. I'll tell you about extremist parties. I'll give you a gift from Hippasus, and last I'll conclude with some guidelines for making and proving claims. Okay, so sets. Okay. So let me write down a few sets. So F equals F(O)x. So typical notation for sets, you open and close curly braces. That tells you I'm talking about a set. Okay, and you separate your elements or your entries in the set with commas. So the vowels are A, E, I, O, and U. Okay, and there's another very particularly interesting set, which is called the empty set, and we write it like this, nothing, or we'll just use the symbol phi. Okay, this is the set that contains nothing. Okay, now it's important that you read chapter 2 carefully. I'm going to gloss over it. It's probably very familiar material to you. So we can do things that we can do things to sets. In particular, we can combine sets to get other sets. Okay, so you should be able to tell me what is the intersection, F intersection V, the elements that are common to this two sets. You should be able to tell me what is the union, F union V. So that's the combination of the two sets. So you take everything in one set, combine it to everything in the other set. Okay. You should tell me you should be able to tell me the complement. So F complement, the complement of the set F. Now that's an interesting one, because basically this is everything that's not in the set F. Okay, well, what's not in the set F is everything else, the whole universe other than these three letters. Okay, so we need to specify what's that universe. And a natural universe in this context is the lowercase letters. Okay, so we could define the universe set, so the set of everything, which is U equals A, B, C, D, E, F, dot, 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 X, Y, Z. Okay, now this is a dot, 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 dot means fill in the blanks. And in this case, it's obvious, you know, it's the whole 26 letters of the alphabet. Okay? You know, we can talk about subsets of a set. So a subset of a set is a set. So the set OX, okay, is a subset of F. And we write that subset or equal to F, subset or equal to F. And what that means is that every entry in O, in this subset, for example, O and X, so O is in F, X is in F. So every entry in the subset is in the original set. Okay. We can ask, what are all the subsets of F? So let's list out all the subsets of F. So now here's something you may not be familiar with. So all the subsets of F, let's start with the one element subsets. So there's F, there's O, there's X, there's F and O. Now the two element subsets, there's F and X, and there's O and X. And then there's the three element subsets, of which there's only one, that's F itself. So F, O, X. So that's the three element subsets. Okay, but there's one other subset that I've left out. Okay, and if you think about it, what's the definition of a subset? Everything in the subset is in the set F. So let's consider this empty set, which has nothing in it. Well, it has nothing in it. So everything that's in it is in F. But it's trivially the case because there's nothing in it. So there's a subset of size 0, okay, which is just the empty set. Okay. So we can talk about the size of a set. In this case, we say that the size of F is equal to 3 because it has 3 entries. Okay. Now all these subsets, okay, there's a notation. So when you're given a set, you can construct all the subsets, and if we collect all these subsets into a set. So I now have defined a set that contains all these subsets. Okay, this is called the power set of F, the power set of F. So we'll use the notation P of F equals this, and that's the notation we use. Some people use the notation 2 to the F, okay, to represent the power set of F, and you'll see why shortly. Because look at the size of this guy. This guy has 1, 2, 3, 4, 5, 6, 7, 8 entries. Okay, so the size of the power set of F is equal to 8, which is 2 raised to the power 3. And that's sometimes why people, use the notation 2 to the F, but we're not going to use that notation. That's a pretty confusing notation, because F is a set. How do you raise 2 to the power of a set? Okay. So one thing to notice about this power set is that it is a set because it's enclosed in these curly braces. But what are the elements? What are the entries? What are the members of this set? The members of this set are themselves sets. So this is a set, this is a set, this is a set, this is a set, and so on. That's perfectly fine. Okay. A set is this sort of universal being, universal discrete object that can contain anything, and even things of different types. Okay, so let me show you another set. Junk is the set hat, car, dog. Okay, these are totally different objects. This is a hat, this is a car, it's a dog, now unrelated objects. Okay, a set can contain very different kinds of objects. So let's call this set weird. Okay, this set weird is the set A, B, C. So the letters A, B, C. And now I'm going to put into this set a set, which is A, B. Okay, so these two curly braces indicate my set weird. But what does my set weird contain? Well, it contains letters and a set. That's perfectly fine. Okay, so a set can contain almost anything. One of the few things that a set, cannot contain essentially is itself. Okay, so that really leads to all kinds of contradictions. But more or less, a set can contain anything. Okay. Now, when sets have this kind of complex form, you can get interesting kinds of behavior occurring. So we say that f. We say that little f is a member of the set F. Okay. So this weird E symbol should be read is a member of. This symbol is a subset of. Okay, so F is a member of big F. Okay, so let's consider the subset A, B. Okay, is that subset a member of weird? Is that subset a member of weird? And the answer is yes. And why is that? Well, because this is an object. It turns out to be a set, but it's a thing. It's a discrete object. It's a perfectly valid entity. And when you look in the definition of the set weird, you find that there's A, B, C. Okay, those are not set. Oh, but there's also the set A, B. So that means this guy is inside weird. Okay, but now, is A, B a subset of weird? And the answer here is also yes. Okay, because look, what does it mean to be a subset? Well, everything in here should be in the set weird. Well, let's look at what's in here. A is in here. A is in this set. And so, is it in weird? Yes. B is in the set. Is it in weird? Yes. Okay. And so, everything that's in the set is in weird, so therefore it's a subset. So, it's possible for a set to be a subset of weird and also a set to be in weird. Okay. This just shows you some of the complexity that can arise when we start talking about sets. Okay, sets can represent very complex things. Okay, let's talk about some of the sets that are going to be the most useful sets for us in this class. Okay, because we're talking about discrete math. Okay, and discrete math is about discrete objects. Discrete objects are things we can count. Okay, and so let's define some sets related to that. By the way, read chapter 2 carefully if you are in any way, unfamiliar with sets. Okay, so useful sets for us. Useful sets. Okay, so the most fundamental set for discrete math, discrete objects, is the set that we use to count. Okay, and we call this the natural numbers. And it's this black bold N, and the natural numbers, okay, start at 1 and 2 and then 3 and then 4 and then fill in the blanks. Okay, you know what this set is, the counting numbers. Notice that we do not include 0. Okay, so some textbooks, if you choose to read other textbooks, will have 0 in the definition of the counting numbers. Okay. But we do not. If we specifically want to add 0 in there, we will use the notation N0, which includes 0, 1, 2, 3, 4, and so on. Okay. But the natural numbers we will define as the set of counting numbers starting at 1. Another useful set for us is the set of integers. Okay. So the set of integers does include 0, but now it's the natural numbers and also their negatives. So plus or minus 1, plus or minus 2, plus or minus 3, and so on, fill in the blanks. Okay, dot, dot, dot. Okay. There's another interesting set, okay, which I'll tell you what it is, but we'll formally define it very shortly, which is what I call the ratios or the rational numbers. Okay, so the rational numbers. So this is natural numbers. This is integers. And this is rational numbers. Okay, so the ratios, okay, so the ratios of numbers, okay, such as, okay, 1/4, 2/7, 3/9, 1/3, and so on. But now the fill in the blanks ... is not clear. Okay, how do you fill in the blanks? Okay, so for this fill in the blank notation, this ... notation is a little bit dangerous. I've used it, to define the natural numbers, and we all know how to fill in the blanks. We all know how to count, and we can count as large as you want. This set doesn't end, so it's an example of what we call an infinite set. Okay. But let's consider some other sets, and in doing so, I'm going to introduce you to a more formal notation for defining sets. Okay, so the even numbers. Okay, the even numbers. E equal to the positive even numbers. 2, 4, 6, 8, ... Fill in the blanks. Okay. So we all know what the even numbers are. We all know what's next, 10, and then 12, and so on. Okay. All right, no problem there. Okay. Let's consider another set. I'm going to call it E prime. Okay, so this set E prime, okay, is 2, 4, 6, 8, and so it's looking like the even numbers. You're thinking, why am I defining the even numbers again? No, okay, so 10, it still looks like the even numbers. Okay, the next is 13, and ... and you go, what? Okay, what? So what is this ... now? Okay, so in this case, we had no problem with the ... Oh, we understood the pattern, it's a familiar pattern, blah, blah, blah. Here, okay, what's the next number here? Is it 15? Is it 17? Is it 14? What? Okay, so you see, a problem arises with this ... notation. It's inherently ambiguous. Okay, now, you let me off the hook with the natural numbers because, that's so familiar to everyone. Okay, I'll let you off the hook for using the fill in the blank ... Okay, but in general, we must avoid ambiguous notation, and so in particular, we must try to avoid this fill in the blank ... because, for me, fill in the blank might be obvious, but then for someone else, it might not. Okay. And in this case, it seems like it might be obvious for everyone, but in this case, it's not obvious for anyone what that fill in the blank means. Okay, so we have to avoid the ... Okay, and one way to avoid the ... is to use what we call a variable in the definition of the set. Okay, so using a variable to define a set. Okay, and I'll start with the even numbers, and I'll show you how we will then be able to define more formally without fill in the blank. We'll be able to define more formally the integers, and then I'll show you how we will define the rational numbers. Okay, and then you will be familiar with this notion of using a variable. So the idea is that when we're defining a set, we will define a set in the following way: that the set of even numbers is equal to a set. Okay, so that's why the curly brace. Okay, now I'm going to need a generic way to represent a typical member of this set. Okay, so I'm going to use a variable. So I'm going to use the variable E. Okay, so this is the variable. What is its value? We don't know. It's just representing, okay, a member of this set. And that's the same concept as a variable that you have studied, in algebra. We don't know exactly what its value is. It's just representing a member of this set. Okay. And now I'm going to tell you what properties E must have, and any number that satisfies those properties is a valid E that belongs to this set. Okay. So I use a divider which says, okay, now I'm telling you what are the properties of E. Okay, and what are those properties? Well, E must equal twice, okay, some other number k. Okay, and if you go back to, you know, how is an even number defined? It's twice, it's even, so it's a multiple of 2, and that's where this twice k comes from. So E must equal twice another number k, where k is a natural number. Okay. So, generic member of the set E, it must equal twice k, where k is a natural number. So let's put k equals 1. K can be any natural number. K equals 1. You get 2 times 1, which is 2. So that 2 satisfies both of these properties, and so it's a perfectly valid choice for E, and indeed 2 is in the set of positive even numbers. If we put k equals 2, we get 4, 4. K equals 3, we get 3, 6, and so on and so forth. All the possible choices of k, we generate all the possible values that are in the set E. Okay, so this is the use of a variable in defining the set of even numbers. Oh, okay. Now I'm ready to give you the formal definition of the integers. And I don't need to use fill in the blanks ... So the integers are equal to. Okay, so I need a generic representative z. Okay, and what are the properties that the z must satisfy? Well, z can either equal 0 or z is some natural number. That counts for +1, +2, +3, 1, 2, 3, 4. Or z is the negative of a natural number, okay, where k is a natural number. Okay, so here's a formal definition of z. Okay, and I only needed to know what is the set n. So in other words, here I'm defining the set E in terms of the set n. Here I'm defining the set z in terms of the set n. Okay. And I've only had to invoke the ... the sort of fill in the blank for the set n. And in fact, later on, okay, when we discuss recursive structures, okay, we will give a formal definition of the set n without using the fill in the blank. Okay, now I can also define the rational numbers. The rational numbers, so the generic member in this set I'm going to represent by little r. Okay, and little r is equal to the ratio of an integer divided by a natural number. So I'm going to write that as r is z over n, where z is an integer and n is a natural number. So here I've defined the rational numbers, and I'm making use of the set of integers, and I'm making use of the set of natural numbers. But this is now a very well-defined set. Okay, and now here's one of the convenient reasons why we define the natural numbers to start at 1, because you can divide by a natural number, you can put a natural number in a denominator and not worry about it being 0. Okay. So you can always divide by a natural number. Okay. Formal definitions of sets. Okay, pop quiz. Pop quiz. Okay, so, 1. Define the positive odd numbers. 2. Define all odd numbers. Okay, so pause the video, try to solve that. Okay, I'll give you a couple of seconds. Okay, so if you pause the video and solve it, great, you're a good definer of things. Okay, if not, here, let me do it for you. So, the odd numbers. I'll use little o as a generic member of the odd numbers. Okay, so is equal to where o is equal to 2k minus 1, where k is an integer. Okay, so let's see. K equals 1, you get 2 minus 1, which is 1. That's the first positive odd number. And then k equals 2, you get 4 minus 1, which is 3, and so on. This produces the numbers 1, 3, 5, 7, and so on. Okay, all the odd numbers are simply the positive odd numbers plus the negative odd numbers. So all odds is the set O, where O equals 2k minus 1, or O equals 1 minus 2k, where k is a natural number. Okay, so here I just took 2k minus 1 just like here. So these are the positive odd numbers, and then this is just the negative of that. So this gives me the negative odd numbers. Okay, odd numbers. Okay, so we can define sets. Let's talk about sequences. Look at the speed at which I erase. Whew! Sequences. So let me mention that with respect to sets, order doesn't matter, and we usually don't allow repetition. Okay. So in sets, order does not matter, and there's no repetition. Okay. Now, if we want to talk about sets that allow for repetition of its elements, then we typically say multiset. And sometimes we do like to talk about sets where we allow repetition. For example, if we wanted to list all the ages of students at RPI, that set would have lots of students who are, let's say, 17, lots of students who are 18, 19, 20, 21, maybe some 16, maybe some 22, and so on and so forth, right? And there would be repetition, and we want to have the repetition because we want every student represented. Okay, and that's the fundamental difference between a sequence and a set. So sequence can have pretty much all the things that a set can have, okay? Except that now order matters and repetition is important. So let's consider a sequence of letters TAP. Okay, that's not equal to the sequence TAAP, in which we have repeated a letter. So this and this are different sequences. Okay, and that's not equal to, none of these are equal to the sequence ATP. So this guy and this guy, have the same letters, so they would form the same set of letters, but they are very different sequences because the order is very relevant. Okay, now, we are going to focus mostly on binary sequences. Okay. And you might say, well, then how am I going to represent cap and tap and atep? Okay, well, so, first of all, we have to find a way to represent these using binary sequences because computers only work in binary. Okay. And second, we have a very well-defined way, for example, of converting any kind of object, almost any kind of object, to binary. It's called an encoding. And for text, we have what's called the ASCII code. So let me give you an example. Okay. So and you can look up the ASCII code online. I'm not going to give you the whole ASCII code, but the ASCII code for T is 0111010. Okay, and the ASCII code for A is 0110001. Okay, and the ASCII code for P is 01110000. Okay, so each letter and also other characters like semicolon, slash, and so on and so forth, they all have an 8-bit ASCII code. So an 8-bit sequence that represents T, for example. Okay, and a sequence concatenates these into TAP becomes TAP. And in a computer, we represent that by the concatenation of these 8-bit sequences. Okay, so when you concatenate all this, so that also introduces this concept of concatenating. You just list this sequence followed by this, followed by that. You get one huge 24-bit sequence, and that 24-bit sequence is the ASCII code for TAP. Okay. So we will focus mostly on binary sequences, but that's without loss of generality because all ASCII characters can be converted to binary, no problem. Okay, and then you can represent it on a computer. Okay, so sets, sequences. The main difference is in sequences, order matters, repetition is important, and so on and so forth. Okay. Now, graphs. Okay, so graphs. Graphs are very important. We are going to spend 2 whole lectures later, but for the moment, a quick overview. Now, in a set, you can put almost anything you want, but a set is not good at representing relationships. So it doesn't show you how the objects in the set are related. That's where graphs come in. Okay, so let's consider some people. Okay, so A, Alex, Bianca, Charlie, David, Edgar, Fiona. Okay. Now, as far as we are concerned, this is just a set of people. We could represent the people as a set. Let's call that set V. So you have the set A, B, C, D, E, F. No problem. Perfect. Okay, but notice how this set doesn't tell you anything about who's friends with whom, and that's because the friendship concept is a relationship. Okay, one way to tell you who's friends with whom is to draw all my objects in the set as little circles that are labeled by the object label. Okay, and I'm going to put a line between 2 people if they're friends. Okay, so look, this line between A and C means A and C are friends. Okay, fantastic. When I just look at this picture here, this picture, I can immediately see who are friends with whom, and I can also see that, okay, well, we have a little friendship clique here and another friendship clique here, and we discussed this in the last lecture. Okay, great. Okay, and this picture, this object here with this discrete object with, people labeled, okay, and links which indicate relationship is what we call a graph. Okay, now it's not easy to feed a picture into a computer. Okay, and so we need some way to represent this graph not as a picture. And what we identify is that the essential thing that's missing from this set are the links. So how would we represent a link? Well, let's think about the link AC. Well, that's just a link is effectively a pair of people. So if I put AC in a set, okay, and typically we don't use the set notation, we simply say AC, so AC, treated as a set, okay, indicates a relationship between A and C, in this case the friendship relationship. So let's list all the relationships. There's AC, there's AD, there's CD, there's DB, there's BE, and there's DE, and then there's EF. Okay, so 1, 2, 3, 4, 5, 6, 7 friendship relationships corresponding to 1, 2, 3, 4, 5, 6, 7 links. Okay. Now, if I collect all of these guys in a set, this set of relationships together with this set of people completely represents this graph. Okay, we typically will, let's call this set E. Okay, and together V and E represent this graph. Okay. And so in order to represent a graph in a computer, all I need to feed the program or the computer is the sets V and E. Let me emphasize that while the formal way to represent a graph is the set V and the set of relationships E, sometimes it's much easier to reason, to think about the picture. For example, if I asked you how many friends does D have, you just look at this picture and say, oh, there's 1, 2, 3, 4 links connecting D with other people, so 4 friends. Okay. Technically, you can extract exactly that same information from the set of friendships. You just see how many of these friendship pairs does D appear in. 1, 2, 3, 4. And there you go. So that means that D has 4 friends. Okay. Let me show you another graph. Okay. And this graph is E, B, D, F, and then A, C. Okay, so F is a friend of E, E is a friend of B, B is a friend of D D is a friend of E, and then D, A, C are friends. Okay, so look at that. Another graph. Perfectly fine. I have people, label, and links. Okay. And if I would ask the question, well, is this graph the same as this graph? You might say, look at them. They look totally different. And that's the point. Okay. Okay. What makes a graph are the sets V and the sets E. And if you think carefully about this graph, okay, the set of people are the same. And now look at the friendships. AC, you know, ADCD, ADCD, DB, BEED, DB, BEED, and EF. All the friendships are the same. So this is the same graph. It's the same graph. Okay. So take note. You can draw graphs in different ways, and it can still be the same graph. What matters are the set of people, or the set of objects, and the set of relationships. Now let me show you a couple of things that we can use graphs to represent. Graphs can represent many different types of relationships. Okay, so affiliation graphs. So the name is not important, but the concept is fairly common. So our friends, our people, A, B, C, D, and E are taking courses 1100, 1200, 2200, 2300, and 2400. Turns out that at RPI, you know, these are very common core CS courses. Okay. Now, A is taking 1100 and B is taking 1100. So, first thing to notice, okay, this graph has objects and they are labeled of different kinds. Perfectly okay. So we have people and courses. Okay. And the link, okay, is linking a person to a course. Okay. And is telling you which courses is A affiliated to. Okay, that's why it's called an affiliation graph. Okay, and B is taking 1100, and similarly we can say that C is taking 1200 and 2400. Okay, and D is taking 2200 and 2400. Okay, E is taking 1200 and 2200. Which is technically not allowed. You're not allowed to take Fox and data structures at the same time. You have to take data structures first. So we don't know how E got into 2200, and let's put F also in here. And F is taking 2300 and 2400. Okay. So you notice how in an affiliation graph, all the links go from one type of object to the other type of object. Okay. Okay. Now, that's nice. Okay, but now let's say you're coming to design the exam schedule for the classes, and you're thinking, you know, what time can I set the exam for 2400? And you observe that 2400 and 2300 have the same student F. Okay, and so, you know, whatever time you set for 2400, you have to set a different time for 2300. If you set the same time for 2300 and 2400, those two courses conflict, those two exams conflict for F. Okay, and so we will say that these two courses are conflicting courses because a student is taking both of those courses. Okay, so we can represent a relationship between courses called the conflict relationship. So if we list the courses 1100, 1200, 2200, 2300, and 2400. Okay, so what I pointed out here is that F introduces a conflict between 2300 and 2400. So there's a conflict relationship between those two courses. If we look at all the other students and what conflicts do they induce, so E induces a conflict between 1200 and 2200. So these two courses cannot have the same exam slot. And D introduces a conflict between 2200, 2400. Okay. Okay. You don't have to draw the links as straight lines. Okay. Perfectly valid to show the link as a curved line. And C introduces a conflict between 1200 and 2400. So 1200 and 2400 has a conflict. Okay. B doesn't introduce any conflicts because they are only taking one course, and A is also only taking one course, so no conflicts. Okay? And so this graph, which represents a conflict relationship between the courses, is called a conflict graph. And this just shows you that you can derive another graph from some other graph. You can derive one graph from some other graph. Okay? No surprise that it's called a conflict graph. Okay, good. So now we have seen the three main types of discrete objects that we will talk about in this class: sets, sequences, and graphs. Okay, let's talk about proofs. And I just want to ease you into proofs to give you a feel for what it takes to convince someone that something is true. So again, speedy race.